Fine. So let's say this is the case where there is a block. It's a wooden block on a surface over here, which is kept it stationary, which is mass is m, and the velocity of this bullet is block is stationary, and there is a bullet which is coming towards that direction with the speed 150 meter per second towards that direction. And this is the mass of this bullet. What happened? This is actually that before that impact. So what will happen when they will collide? This bullet will be embedded inside that block, which means it will be inside that block, and it will be not passes through the block actually. All right. So it will be inside the block. I'm going to draw this one. This is a bullet, and after the impact, what they did? They move with a common velocity, and after traveling a distance, which is actually, let's say, the d, it is stopped over there. Its final velocity is equal to the 0. Let's say this is actually the initial velocity. Now they ask over here two questions. No, not the two questions, simply one question, that frictional force. So what is the frictional force over here actually? How much frictional force is going to act on this block when they are going to moving at that distance d? Fine. To solve this one, there is some other information is given. This d is given, which is 270 centimeter, 270 centimeter, and the mass of this block, capital B for block actually I'm using, which is actually that 2 kg, and mass of the bullet, which is small b, which should be 5 gram, and the speed of that bullet, which is 150 meter per second. Now they ask me what is the frictional force acting on that part. There could be a lot of questions should be asked over here. So initially I'm going to excuse me, finding out only the frictional force acting on that block. Fine. So to find out the frictional force, if you draw the free body diagram, look at this. This is I can find out the frictional force if I just know that, because frictional force Fk actually is simply that mu k into n, right? But that mu k is not given over here. Probably they will also ask you find out the mu k from there. So in a tag question, that could be also asked from here. All right. So that's why I need to draw the free body diagram over here. If I draw the free body diagram, this is actually that gravitational force, which is the downward, and in this gravitational force we have both actually bullet mass and the block mass, right? We have to consider both two mass actually, the mass of that bullet plus mass of that block, because they stick together. Stick together means this is a completely inelastic collision, right? Am I right? If it is stick together means they completely stick together over here. Fine. So this is my this is would be normal reaction force. This is would be frictional force over here, and in this direction it doesn't have any force. It has only the velocities, the vi. Now, since it's a frictional case, so what I cannot write down the total energy over here is not giving the total energy at final point, because there is a frictional force present into the system, which means this system would be a non-conservative system. Fine. Then what I can write, I have that one more theorem, which is actually we say that work energy theorem. I can write net work done of the system would be simply change of kinetic energy, right? I can write it should be change of kinetic energy. Now net work done, if you write down, there are three forces over here: work done by the normal force plus work done by the gravitational force plus work done by the frictional force must be actually kinetic energy final minus kinetic energy initial. Kinetic energy final of the system is going to be the 0, right? It would be 0. Work done by the normal reaction force and work done by the gravitational force, it will be also the 0, because these two forces actually makes an angle 90 degree with my displacement. So that's why cos 90 actually the 0, so their contribution into the work would be 0. Fine, then what I'm supposed to write? So work done by the frictional force must be equal to minus kinetic energy initial, right? Then work done by the frictional force, I'll write Fk, this is my force, this is the displacement, and that is the angle between these two vector, which is cos of 180 degree, minus half of mass of these two object, mv plus mv into vi square, right? This is the kinetic energy. Then I can also drop this minus sign, because cos of 180 degree will be minus 1. Then I will find out Fk would be d equal to half of mb plus mb into vi square, right? From here I'll be able to find out the Fk. To find out the Fk, I need to know this parameter: mass of the bullet, mass of the block, and the velocity of these two systems after the impact, divided by 2 into d. I know this parameter: mass of the bullet, mass of the block, and the distance the bullet and block system travel, but I do not know that velocities of this system after the impact, right? Then I have to use to find out this Vi from there. So if I want to find out this frictional force, then definitely I need to know that force, I need to know that velocity of that system after the impact. All right, so to find out that velocities, I'll use that idea of momentum conservation over here. So momentum will be conserved whether there is an elastic or inelastic collision. Then I will write that initial momentum must be equal to that final momentum. Initial momentum, so momentum of that bullet, which should be mass of the bullet into velocity of the bullet, plus mass of the block into velocity of the block. It should be, because after the impact they stick together, mass of the bullet, mass of the block into that v velocity, which is I over here, right? I'm writing, you can write down in notation. So it's a vi. It's not the initial velocity, it is actually that velocity after the impact I use over here. This one is going to be the 0, right? Because the block was initially stationary, so that's why it would be 0. Then I can find out this vi is simply going to be that mb vv divided by mass of the bullet plus mass of the block. You can plug in this equation into that equation 1, or you know everything, you can find that initial velocity, I'm sorry, is the velocity after the impact. And if you can find out that velocity after the impact, you can write down this into this equation to find out that frictional force into this equation. And not only that, if you know the frictional force, then you will be also able to find out that coefficient of kinetic friction, which would be Fk would be simply Fk, mu k would be simply Fk divided by n, right? If you know from that equation, you will be able to find out that part from here. So, or I can write down. So this is would be Fk, actually that part which is this one I'm writing for you. So this is going to be that half of mb plus mb into vi square. Vi is this one, which is mb, mass of the bullet, divided by m plus mb whole square, right, divided by n. N should be that mb plus mb into the g, right? Then you can neglect this part. This should be cancelled out. I'll be able to find out this mu k is going to be the simply, I'll simply write mb square 3b square divided by 2 into g into mb mb plus mv square. So that should be that coefficient of kinetic friction between the block and the inclined plane. Right? Do you understand? You can solve in that way. Alright, is there any question over here? On guys, speak up.
No, sir.
All right. Let's do another problem. Let's say I have an inclined plane on a curvature track. This is actually not the inclined plane, on a tabletop, and this is actually completely frictionless case actually over here. Let's say this is a block I kept over here, which has a mass actually, that small mass, and this one has a height actually, the h, and I release another mass from here, from the rest to the 0, and this total system actually above a table which has height of this table actually, let's say capital H, is that height of this table. What happened when you release this curvature track actually, the friction layers, if you release that system, what's going to happen, this one will be slide down over here, and they'll be make a collision over here, right? And after the collision, what will happen, probably they can bounce back. If their velocity is negative, they'll be bounced back, and they can also fly off from the table actually. Now the question is, if they fly, where they will be fly, at what distance they will be fly over here. That's the question over here. This is the bigger mass, and there is a condition is given, this smaller mass actually half of this bigger mass. Alright, so that's means the bigger object is going to be this strike a smaller object. Fine. So this is another comprehensive problem actually I'm doing over here for you, which may I have to find out if they fly off, then I have to find out the distance actually. This is the distance for bigger mass. It should be velocity of the bigger mass into the time, right? And distance for the smaller mass, it should be velocity of the smaller mass into the time. T is same over here because they are flying more, traveling the same distance, and they actually start from the 0 velocity in the vertical direction. So that's why their time of flight will be the same, because they don't have any velocity towards that y direction actually. initial moment. All right, so so first of all, we can find out the time using this y vertical displacement. But before that, we need to know these velocities of these two blocks, which is the Vm and the V small m, which is the velocity just after the impact of these two systems. Right. So that we can find out using that collision idea actually. So that's why if you want to find out it's a head-on collision, collision 1, then I'll write down that velocities of that bigger mass, or I can write in that form actually, so it would be easier to correlate it with you. Let's say this is my object 1 and this is my object 2, smaller mass actually is object 2. Then I'll write that formula I give you. So since it's a head-on collision, I'll write this part V1F, it should be m1 minus m2 divided by m1 plus m2 into v1I plus 2 m2 divided by m1 plus m2 into v2I, right? This is the first equation. Now over here v2I, that's mean the initial velocity is 0 because initially that second object is stationary. So that's why I can drop this part from here. And also true for this v2f, it should be 2 m1 divided by m1 plus m2 into v1I plus that part will be also the 0I. So that's why, or I can write this would be m2 minus m1 divided by m1 plus m2 into v2I. This part is going to be the 0 over here, right? Now I know this m1 and m2 because my m1 actually that bigger mass and m2 actually that which is the smaller mass, small m, and that is smaller m actually that half of m2, right? That's the condition is given? Yes, smaller mass actually the half of this bigger mass. But then I need to know this v1I. Now what is the v1I? v1I actually that initial velocity just before the impact. So that's mean which is the first velocity of this first object m1, not over here, it is 0. The velocity is gain because it has the potential energy. That velocity is going to be gain over here, makes a kinetic energy. Because it's a frictionless, that's the kinetic energy will be strike over here, which means that should be actually the initial velocity for this system. It means that I need to use another idea over here, which is the work energy theorem, right? Or conservation of the mechanical energy. Since it's a frictionless.
Sir, initial velocity টা একটু আরেকবার বুঝাই দেন।
So initial velocity is the velocity we say that of a system just before the impact, right? Right?
Yes sir.
So
Yes sir.
once you release the block that has the potential energy, it will be converted to the kinetic energy, and at that kinetic energy, that block m is going to be strike that smaller block, right?
Yes sir.
That should be the vi, which is the initial velocity of the system before the impact.
মানে স্যার নিচে আসার পর।
Yes, exactly, because that would be the velocity. At that velocity, it will be going to strike with the smaller mass, right, or m2.
Yes sir.
So that's mean I need to also use that mechanical conservation of the energy. I'll write EI should be EF. So its kinetic energy initial plus the potential energy initial must be kinetic energy final plus the potential energy final. Initial kinetic energy of the block is 0 because it's released from the rest, and final potential energy of the system will be also the 0. If we choose, that's my actually the surface or origin over here. Come on, my system is disturbing. Alright, so if I choose this is my reference level, and at that level the potential energy would be 0, you can consider, which is mgh. Since h is 0 at that level, so that's why it will be 0. Fine, then I can write which means potential energy is simply that potential energy of that block, which is mg, this one, a capital mg smaller s, would be converted to the kinetic energy of the block, right? That's the thing I'm going to write over here. Then I can write this should be mgh must be equal to half of mv1I square. That's the velocity actually, or vf, whatever you can write. I'm writing at a time actually. This capital M will be cancelled out from the two sides. Then I will find out v1I would be simply root over twice gh, right? Now I can plug in those part actually into this equation. If I include that part, what I'm going to get from these two equations, right? I write it over here. So v1f, I have that v1f, which is m1, right? m1 minus m2 divided by m1 plus m2 into v1I. So m1 actually that bigger mass minus m2 actually the smaller mass, which is m by 2 divided by m plus m by 2 into root over twice gh. From here you can find out what would be that case actually. It should be probably Vf would be what? I can say, let's check that. It should be, if I factor out, it should be 1 minus half divided by 1 plus half into root over twice gh, right? If I just factor out the m from numerator and the denominator, so v1f, then I will find out this v1f is going to be that it's a half divided by 1 minus half is definitely going to be that half, and 1 plus half is going to be 3 by 2, right? I'll get actually that 3 by 2 to root over twice gh. You can neglect this 2, and you will find out this v1f would be simply 1/3 2gh, right? This would be my v1f. Now what about that v2f? v2f is going to be simply 2 m1 divided by m1 plus m2 into v1I. Then I will find this v2f is going to be that 2 into m1 is the bigger mass and this is going to be that m plus m by 2 into root over twice gh. Then I can also neglect that this m from numerator and the denominator. You can write, come on, so I can write this v2f is going to be that 2 into 3 by 2, right? Am I right? Into root over 2gh, then we will find out this v2f is going to be that simply 4 by 3 root over twice gh. So that should be that velocities. And remember, this is the velocity of that second object. I can say v1 f, which is simply vm, right? And that's I find out 1/3 root over 2gh and v2f actually would be velocity of the second object, which is 4 by 3 root over twice gh, right, which is means the smaller object has a bigger velocity. Of course it has a bigger velocity. It is the 4th time of that smaller mass, because mass is also that half of that one, right? Fine. So now,
Yes, sir.
fine. Now, if I want to find out this xm and that x smaller m, I have to find out the time, which is the t over here, right? To find out the t, I'll write it should be y should be y naught v naught yt yt plus half of ay excuse me, ayt square. This one is 0, this one is also going to be the 0. Then I can write this should be simply, it's a minus capital H equal to minus g by 2 into t square. I don't see the plug in the value of g, so I'm doing analytically this part, so I can neglect out this minus sign. Then t should be square root of twice h divided by g, twice h divided by g. So that should be that time period of these two blocks. Alright, to find
স্যার
out,
ব্লক দুইটা কি টেবিল থেকে পড়ে যাবে?
because the velocity is positive, both two are velocity
Oh.
positive. Positive means both two system will be towards that forward direction, because it will be have that direction. If you find out any velocities v1f and v2f actually in the negative, then it should bounce back, it will be moved in the opposite direction. Alright, now you can write, so xm, I can write the vm into t, right? What is the vm? Vm actually 1/3 is a 1/3 root over 2gh into the t is root over 2h into that g. That's the case. And xm actually that vm into t, vm actually 4 times of that root over twice gh into the t 2g, this one, right? Now can you tell me from this two equation which block will be cover the larger distance, smaller block or the bigger block?
Smaller?
Of course smaller block, right? Because look at this, it has 4 time of that part. Is that this thing is exactly the same, except if I factor out this 4, it is exactly, I can write this would be that xm. So that's why smaller block will be travel the 4th time of bigger block. And now I can also ask you what should be the average velocity and what velocity they are going to strike. Those are actually you can find out. That's called actually comprehensive problem, right? With this, to solving this one, I use that energy conservation idea, I use the momentum idea, and I also use that
এনার্জি কনভার্সনের যে আইডিয়াটিকটা অ্যাপ্লাই করবেন করলেন ওই লাইন ঠিকটা আবার একটু বলবেন জাস্ট খালি ওই লাইনটা
you say total energy must be the conserved, because the initial total energy must be the final kinetic total energy, mechanical energy, because this track I said is a frictionless. Then whatever the energy it has at top point, and that would be also equal at the bottom point, there will be no loss of energy over here. Since it's a frictionless, that means the system is conservative system over here. So that's why I write down kinetic energy plus potential energy at the top point must be equal to kinetic energy at the potential energy at the bottom point. Initial kinetic energy will be 0 because I release from the rest, and final potential energy would be also the 0 because I level, this is my actually that 0 reference for this height, right? Because if I neglect, consider this is a height h, we are referring from that point, reference point, right? From that part actually I find out velocity, initial velocity of the block, which is that this one, u9. All right, so is there any question over here? Any more question? Come on guys, time is running out. Fine, so that's last, keep that part. Last problem I'm not going to do that. I will try to make no, it has to be two because it's a two-dimensional problem actually. Not I'll upload a video regarding that, if any problem is needed more than that actually from this chapter, but I need to start right now. Rotational part actually, rotational motion. All right, let's start that rotational kinematics over here. Rotational kinematics. Not only the kinematics, I also talk about the dynamics at a time because we don't have enough time, right? We have only 2 classes in the next week actually. This is the last week. All right, so to study that rotational motion actually, we need to concern about the kinematics as well the dynamics part of the system, because rotation system is a rigid body actually. Let's say when a disc is rotating about its center of mass, we have that idea of that, then it has some angular velocity, then there will be a lot of things we can express, or a lot of information we are going to get from this part actually. First of all, I want to define that rigid body. Rigid body is that body if the distance between the two point mass of that system is is constant, then it's called actually the rigid body, which means let's say I have any arbitrary shape of object. Let's say this is my 2 point mass into that rigid body. This is 1 point mass and another point mass would be over here. Let's say this one. I say this is the ith point and this is the jth point over here. So this is the jth point. If the distance between these 2 point mass, which is Rij, if I write Rij, is also you can write from the displacement, is constant. Constant means that these 2 points is not going to be displaced at all, right? Whatever the force you apply, it doesn't change this position of these 2 points, which means that distance between these 2 points actually the fixed. That actually called the rigid body of the system. This means these 2 points, whatever the force you apply, these 2 point mass is not going to change their position. That call actually that rigid body. And in this rotational kinematics, we will only discuss about that rigid body system actually, rigid body kinematics and the dynamics part actually. All right, to describe the kinematics part, we need to introduce some parameter. First one we can say that is a angular position. It look like exactly the analogous to that linear kinematics we will use. So let's say this is a rigid body. On that rigid body you have a point which is you are rotating this rigid body, you mark that point and you rotating that point, and that location of this point actually that theta I actually that initial angular position actually, this one we say that. And after a certain time when is going to rotate this one, this point should be moved from here to here. Let's say this is that final point in a particular time, is travel from here to here, which means that is create some angular displacement at the center, which is actually the theta, we say that. And this theta, we say that angular displacement of the system, and this angular displacement should be in radian. we will express this angular displacement will express by that theta, which should be theta f minus theta I. Sometimes we also say that the del theta is the difference between this angular position, and this del theta should be in radian. Remember this part for this rotational motion. And this, let's say this disc is start from there and goes around and come back its initial point, then its angular displacement in that case it should be twice pi, right, which makes a complete rotation, is called the complete rotation, or you can say that actually the 360 degree. So there are some relation between, and in this is also called the one revolution, actually one rev. In short note we write down one revolution, right. So one rev actually is 360 degree or actually that twice pi radian, right. This is twice pi radian. From here you can find out the relation between the radian and that degree. 1 radian should be 57.3 degree. You can write 1 rad should be 57.3 degree. Come on. This is the relation you can use from rad to the degree. All right, so right now if I know that angular position, then I will be able to find out that angular velocity. Angular velocity I will express, which would be angular displacement over time, right. So we can write, let's say a system has traveled from one point, from let's say starting from that point, and it goes over here, and at the same time it's creating angular displacement, which is actually that this one theta or sometimes you can say that del theta is a del theta. You can say that it's travel this del theta at the time t, then this angular velocity you can write it should be omega we express by the angular velocity by the omega, which should be del theta divided by del t. Right, so that's called that angular velocity, and unit should be rad per second, right. And sometimes this velocity we also say that average angular velocity also, because I am taking, look at this, is a del theta divided by del t is called that average angular velocity. We can also find out instantaneous angular velocity. We know that instantaneous velocity you have to take that derivatives. We write what's wrong with the system? Instantaneous angular velocity which would be simply we can write down omega should be d theta divided by dt. Is exactly look like that linear instantaneous velocity. In that case we write down the dx over dt, right. So its unit would be also rad per second. And the same way we can write that angular acceleration can write which should be angular acceleration we can write that should be expressed by that alpha. Alpha should be del omega over del t. Del omega over del t, and its unit should be rad per second square. Rad per second square. And instantaneous is sometimes this is also known as average angular acceleration. Also, this one is called that average angular acceleration. You can also say the same thing. Now, instantaneous angular acceleration, we can also write down is alpha should be d omega over dt, which means that we have to take that derivative of that angular velocity function. We can also write down this one would be d theta square over dt square, right? So that should be that angular velocity of this part. All right. So this is actually we can write down. It is pretty much similar to that linear case actually. It's wrong. That is disturbing. So then we can make a relation from this part. This alpha actually del omega over del t, right? And del omega we can write omega f minus omega I divided by del t. From this equation we can write omega f minus omega I equal to alpha into del t, or we can write this omega f should be omega I plus alpha into del t, right, which is exactly analogous to that your linear kinematics equation, which is Vf equal to Vi plus At, which moves at a constant acceleration a. Right now this system moves at a constant angular acceleration actually, that alpha. Right, so that's mean it is also we have that similar type of equation for that linear kinematics for this rotational kinematics. So that's why I'm going to make this comparison of the equation over here. If you write down the linear equation, and right hand side I'm writing that angular equation or angular kinematics equation, angular equation over here, I can write, let's say if we express that linear displacement by the x, then angular displacement would be theta. Linear velocity is v, angular velocity will be expressed by the omega, linear acceleration is the a, then the angular acceleration is the alpha. There is a relation between these two parameters, a and alpha. I'll show that one. And if the system moves at a constant acceleration alpha, then we can write actually make Vf actually for linear case Vi plus At, which moves at a constant acceleration a, and x equal to x naught V naught xt plus half of a xt square. This is the general displacement equation, and Vf square equal to Vi square plus 2 into x or del x. Sometimes we say that this is actually the system kinematics equation if the system moves at a constant acceleration a. Same thing we can write for the angular part. Omega f should be omega I plus alpha into del t, and final angular displacement should be initial angular displacement plus omega I t plus half of alpha t square, and for velocity part we'll write come on, my system is disturbing today. Why? It's not responding. Why? Oh God, please help me. Too slow. I need to change the system. Alright, so omega f square I can write omega I square plus 2 alpha into del theta. So those are the system if it is moves at a constant angular acceleration alpha, right? Alright, now there are some new parameter we are going to write down over here. First one, if we express the mass into the linear case, actually expressed by that m, and in that rotational part or rotational kinematics, that quantity or the mass will be expressed by that letter, actually that I, that's called actually that moment of inertia. This is the new parameter actually we define, and it is very important for this chapter actually. That's we call actually that moment of inertia. This is, I'll define what is that. Just I'm writing and if you write down the force, which is actually the ma for the linear part, for angular part will express by the twisting force is called the torque. Torque equal to I alpha, because I said mass is analogous to the I and A is analogous to the alpha. So that's why torque would be I alpha. This is also called the Newton's second law in terms of rotational motion. And the linear momentum we express mv and then angular momentum will express L should be I omega. I omega, and that force if you express the force if you express the force by that fa ma actually, then work we can write F into D and in the case of rotational part we will write down that torque into theta and the kinetic energy, which is right half of m vv square, and for rotational part, rotational kinetic energy we will write that should be half of I omega square. Those are the parameter actually we need to understand to describe the rotational motion of the system, because this thing would be new for you actually. So that's why we'll discuss this part over here elaborately. Fine, but before that we need to make a relation with that linear acceleration to the angular acceleration. We know from the rotational part or rotational motion, we say that v actually that omega r, right? We know that equation. Then if we take the derivative of this equation on the both two sides, it will give me dv over dt, and it should be d omega over dt into r plus that part would be 0, because second time if you take the derivative of the r, so derivative of the r would be 0 because r is constant over here, right? Then I can write dv over dt is simply that a, it should be that a is going to be that d omega over dt is the alpha into r. So that's also the relation between your linear acceleration to the angular acceleration. This equation is very helpful. We need to sometimes use that acceleration has to be transferred for that linear acceleration to the angular, and that acceleration actually tangential acceleration. Remember this part, because remember when a system moves towards that circular track, right, we have that velocity actually that v tangential to the path. Actually every time it should be tangential to the path in that direction, which is actually that v, and that acceleration is also called that acceleration towards the tangential to the path. That's why sometimes we can make a relation with that linear acceleration to that angular acceleration using this equation. Alright, now let's focus on this angular part actually, which is we are going to talk about that rotational part. To describe that properly, I need to that concentrate those rotational parameter over here, which is first one, we say that moment of inertia of a system. Moment of inertia of a system is described actually how hard to rotate a system actually. First one, I'm going to define that moment of inertia. The first thing I'm going to define over here is would be simply that moment of inertia. This is a very important concept actually. Moment of inertia is going to tell you how hard to rotate a system. That means how much energy does it require to rotate about a point, about a rotational point, because if it is required more energy, then it is going to be the hard for you to rotate the system with some angular velocity. If it is required less energy, then it would be easy for you to rotate the system, right? So that's why I'm saying that it will tell you how hard to rotate the system. If the energy is high, then it will be hard for you. If the energy is low, and then it will be easier for you. So that's mean in that case you have to apply less amount of energy to rotate the system, right? Fine. Now then how you are going to calculate that this moment of inertia of a system, or how we are going to find out? Let's say you have this point mass, and this point mass at a distance from a rotational axis. We say that this is actually the rotational axis. This line I draw over here, it should be our rotational axis. Then this mass is at a distance actually that r. This is my mass. Come on. This my mass is m, and which is rotating around this circular track. What is disturbing? Then moment of inertia for this point mass, we are going to simply find out using this equation. I should be mr square, which means it is the directly product of these two quantity, mass and the distance from its rotational point to the position of that mass. Alright, that's called actually the moment of inertia for the point mass distribution, and unit should be, from this parameter you can find out, it should be kg meter square, right? It should be kg meter square. And what happens if you have more than one mass? Let's say I have this mass and I am labeling this one. Let's say this is R1, M1. I have another mass over here. This is M2, and R2 is the distance. This is M2 and R2 is the distance. I have another mass which is in that side, which is M3 R3 R3, and I'm going to rotate this system about this axis actually. Then the moment of inertia for this 3-point mass, I'll write I should be M1 R1 square plus M2 R2 square R2 square plus M3 R3 square, right? So that's if I have more than 3 mass, let's say I have nth mass on the system, then I will also write down so on. So this one I can write down in terms of summation notation. Since I have 3-point mass, then I can write it should be I 1 to n. I'll write this one actually I 1 to n. It should be mi r square. If I have nth particle into the system, then that should be actually the moment of inertia for this point mass distribution. We'll use this equation for the point mass distribution. But if I have a continuous mass distribution, let's say any arbitrary shape of object, if I want to find out the moment of inertia about any rotational axis about any point, let's say I'm going to rotate about this axis, then how I'm going to find out the moment of inertia for this type of object or this shape of object, continuous mass distribution? Then what I'm going to do, I'll choose a point mass distribution over here, which is, let's say this is actually the dm, and it should be at a distance actually the r from this rotational axis, because this is the rotational axis is rotating about that axis r. Then if I want to find out for whole mass distribution, which is continuous mass distribution over here, then I will simply integrate that system to find out the total moment of inertia for this object. So then I will write down this should be simply if I write down this dm into r square. But if I want to find out for whole mass contribution, in that case I am going to simply integrate this part. I will integrate this part to find out for total system moment of inertia. Right, so that's how we will use this equation to find out the moment of inertia. This one we will use for point mass distribution, and this one we will use for continuous mass distribution to find out that moment of inertia of a system. Alright, let's say I am going to draw a system over here. My system is disturbing today. I don't know what is the reason. Let's say I have 3-point mass over here, which is 1, 2, and let's say this is the 3. This has a 1 kg. This middle mass has a 2 kg, and this has again the 1 kg mass, and they are connected by 2 massless rod. Actually the length of this 2 rod, this is actually that 1 meter, and this is actually the 2 meter. 2 meter from here to here, actually this from here to here actually the 2 meter, and this one from here to here actually that 1 meter. Now I want to rotate these 3 objects about this 3 point A, B, C, and I want to check that through which point it would be easier for me to rotate the system. So easy would be the point which has a lowest moment of inertia. Through that point it would be easier for me to rotate the system with some particular angular velocity, right? Let's say I'm going to choose this axis and this axis and this axis. I have to find out the moment of inertia for this system throughout these 3 points. I will calculate the moment of inertia throughout the point A. Then I have to consider from here is a, I will use this equation actually, since it's a point mass. I am going to write in this equation I should be summation I1 to n, which is the index. It should be mi ri square, right? So this should be actually that formula I am going to use over here. Then 1 kg actually at the origin, so that's a distance is 0 plus 2 kg at a 1 meter away from my rotational axis plus 1 kg is 3 meter away, right? From here I am considering the moment of inertia from this axis, which is the axis A. Then it will give me 9 plus 2 is going to be that 11 kg meter square. Now throughout the point B, I will write 2 into 0, because right now this axis 2 is already its origin, that is why r is 0, plus 1 into minus 1 square, because if I choose the origin this one, then this 1 kg at a minus 1 displacement, plus 1 into 2 square, which means is going to be that 2 square 4 or 4 and plus 1, this is going to be that 5 kg meter square, right? And for the point C, I will write it should be 1 into 0 plus 2 into 2 square plus 1 into 3 square. Then it's going to be that 2 square 4, 4 into 2 8, 8 plus 9 is going to be that 17 kg meter square. Throughout these 3 points, throughout the point B has a lowest moment of inertia. So that means it would be easier for me to rotate that system about the point B, because it has the lowest moment of inertia of the system. And why it is so? Because this B point would be also closest to the center of mass of this system. So that's why it will be always true that throughout the center of mass for every system has the lowest moment of inertia, and that's why it would be easier for us to rotate any system throughout the center of mass. In that case, it would be required less amount of energy. That's why when you throw something into the air to rotate, it will be always try to rotate throughout the center of mass if it is free rotating. So if you rotate anything into the air or the free hand, it definitely is going to rotate about its center of mass, because in that case it required less amount of energy to rotate the system. For this system I create over here throughout the point B, it would be easier because this B point would be also closest to the center of mass. So that's why throughout the point B would be easier for me to rotate the system. Alright, let's consider I have a continuous mass distribution of the rod, which has a uniform distribution of the mass. So which has a mass is m and the length is L. I want to find out its moment of inertia throughout the 1n. Let's say this is the 1n I am going to rotate. This is a left side. You can say that throughout the left side I want to find out what should be, if I rotate about this point, then what should be its moment of inertia. Alright, to find out this moment of inertia, I have to use that continuous mass distribution formula, which is actually I write it's a dm into r square, right? This is the formula I am supposed to use over here. For that one I need to choose this is actually the differential element of the mass dm, and this void of this mass actually the dx or the length, and this dm mass actually at a distance x from my rotational axis. Now I can say that moment of inertia for this differential element of mass, which is the dm at a distance x square, right? That's with the moment of inertia for only for this differential element of this mass. But if I want to find out for whole rod, what I have to do, I have to integrate this rod from 0 to L, right? That should be the formula to find out this one. But the problem is I cannot integrate these two parts because I have these two different parameters. One is the mass, another is the distance. So I will use that definition over here is called that linear mass density. It look like exactly from the center of mass we did for that case. We write that lambda, it should be mass per unit length dm over dx. If I take the ratio whatever it is, if I take the total mass divided by total length, it should be exactly the same ratio over here. All right. Then from here I can find out this dm should be lambda into dx. I'm going to plug in those information over here. If I plug in, it should be 0 to L, dm should be lambda into dx into x square. Now I integrate this part because both one actually the same parameter, dx is also the length and x square is also the length, right? Then I am supposed to write one more line is going to be that lambda is out. I factor out that part, 0 x square into dx, right? You can keep in that part. It's not working, this part. Can you give me 5 minutes extra, guys, so that I can finish this part I started right now? Would it be possible for you to give me 5 minutes more?
Yes, sir.
Yes, sir.
All right, thank you very much. Also, I'm sorry, my system is disturbing today. I do not know what is so. All right, so give your attendance, guys. Write down your name and ID first into this chat box.
স্যার এটা ফাইনালি হবে কি ml স্কয়ার বাই 3
Moment of inertia, yes, 1/3 ml
আচ্ছা।
square.
হ্যাঁ ওটাই আসে।
Please give your attendance. Write down your name and the ID. Need to check that one. Why is disturbing? Alright, so let's, because my system is not responding actually today. It's very disturbing. Alright, this probably is going to the work. I do not know. Seven two. Alright, from here we can write this I should be, if you integrate this part, it should be lambda, so it's going to be that x is cubed by 3, right? It should be 0 to L because if you plug in the 0, that's going to be meaningless, so it should be lambda into L cubed by 3. Then I can write this I should be lambda, I can replace by m by L, and it should be L cubed by 3, which it will give me, I can cancel out 1 L, it should be simply 1/3 ml square. So that should be that. moment of inertia for this system. Throughout the left side actually, we write it should be 1/3 ml square. Same thing you can find out for the right side. If you write down for the right side, I R, it should be 1/3 ml square. You can do in another way. If you instead of left side, if you do the right side, it will be also exactly the same, right? You can also use that formula if you want to find out throughout that center of mass. In that case, you will simply change that limiting value. You will integrate from minus L by 2 to plus L by 2. Using that same equation, you can find out that this moment of inertia for this system actually, that throughout that center of mass, it should be 1/12 ml square. That's how actually we will be able to find out the moment of inertia for the system. And this is very helpful. We need to understand this part. We'll use this part actually for different case actually. For different shape of object has a different moment of inertia throughout the center of mass, but that could be derived from that part. Most of the case they will give you this part throughout the center of mass. So let's say if you have a disc which has a mass is m and the radius is r, then its moment of inertia throughout the center of mass would be half of mr square through the center of mass. But if you want to say not the center of mass, if you want to rotate about this point, then how you are going to find out moment of inertia? We'll talk about those things in the next class. All right. Thank you very much, guys, for your extra time.
স্যার
Yep.
মিডের মার্ক কবে দিবেন? এক সপ্তাহ স্যার ফাইনালের।
Yeah, we'll get that one. Don't worry, I'm checking that part. I have started.
আর কুইজের মার্ক